Friends, welcome to part 2 of our video presentation on big data. Just like part 1, this part is based on the tutorial by Hugh Watson that is uploaded to your Canvas course page. In this part of the video presentation, we will talk about the technologies that comprise big data infrastructure. Now, as you can imagine, strong data/IT infrastructure is needed to accommodate big data. In fact, when you have a strong data/IT infrastructure in place, you can quickly develop big data applications in a matter of days. But if you don't have a strong big data IT infrastructure that can support massive volumes of data, from various sources created in real time, then you may not be able to pursue any kind of organizational initiatives in relation to big data. Now, previously, companies had problems accommodating big data. However, improvements in various data-related technologies made it easier to store, manage, and retrieve big data sets. And this is what this presentation is largely about. It's about various technologies that typically comprise big data infrastructure. Now, something that is usually at the heart of any kind of big data infrastructure is the so-called scale-out architecture or massively parallel processing architecture, MPP. I think an older term for this approach, for this computing architecture, is called grid computing. So what happens is that you have hundreds or thousands of low-cost commodity servers that work in parallel. So the trick here is that if an organization needs to have a powerful computing infrastructure, they don't buy expensive servers or mainframes. Instead, they buy those low-cost commodity servers or computers, and they connect them together to work in parallel as one big, giant supercomputer. Now, each server has multiple CPUs. Sometimes, most of the time, they have large shared memory cache. Data and processing are both spread across those multiple servers, and they are performed in parallel. So this is how massive, computing power is created, because you have those low-cost commodity servers working in parallel. So vast quantities of data can be stored and analyzed quickly. And also it has an economic advantage. For example, if you need additional processing power, you just buy a few additional servers. You don't have to purchase like a new supercomputer or a new powerful server that may or may not be utilized fully. So this is like a trick or an approach to create powerful computing infrastructure with relatively low-cost commodity hardware components. Also, big data processing would not be possible or would not be very efficient without improvements in some memory technologies. So the two memory technologies that are usually part of big data is in-memory processing and solid-state disks. Now, we'll expand on in-memory processing a bit, but just to give you like a brief overview of that, in-memory processing means you do processing, you do analysis, you do analytics using random access memory as opposed to using disk memory, because this is much faster to do it this way. As you probably know, random access memory is much faster in terms of a central processing unit getting access to it. And then you have another advancement called solid-state disks. This is in contrast to those regular hard drives that have moving magnetic parts. Solid-state disks, they're like one single integrated circuit, similar to the flash technology. And because of that, because there are no moving parts, there is no need to kind of spin a particular blade to find information. It's just much faster. So solid-state disks are usually used as a part of big data infrastructure. Data warehouses are also central to big data. Now, a data warehouse, just like the name says, it's a warehouse for storing organizational data. You see, every organization has a lot of data available, but something that you can quickly learn from your experience is that this data is not easily available for anybody who wants to use it. The problem is that this data, is stored in different parts of the organization on different servers in different formats. It also belongs to different individuals, different organizational units. So although the data is there, it can be potentially used for business analytics projects, it's hard to find. It's hard to find, and it's hard to clean, and it's hard to deliver to the right people. So that's why many organizations are investing into developing data warehouses. So this is like a centralized location where all organizational data is stored. So anybody can go there and retrieve the data that they need for their projects. So at the physical level, you can think of a data warehouse as like a room, that is full of servers, boxes, that store data from various sources. Now, as a part of a data warehousing initiative, data is extracted from source system, let's say, various organizational systems, ERPs. Then it's transformed into clean, consistent format. Then it's integrated, let's say, using a common key with other sources so that you have information about customers coming from different systems, different sources, and then loaded into data warehouse. Then users and applications, they can access the data from the warehouse. And some major vendors that offer data warehouse solutions include IBM, Oracle, SAP, Microsoft, and Teradata. Now, Teradata is an emerging company that is gaining a lot of reputation in this whole area of big data. Data Mart appliances, something that is usually a part of a data warehouse or something that is connected to a data warehouse. A Data Mart appliance is an integrated stack of hardware, software, and storage in a single box, like a single computer or single server. It's built to process queries quickly, queries related to one particular domain, let's say customer information or customer transactions. Typically, they're standalone system that meet a smaller need, meaning like a need of a smaller organization or sub-part of an organization or a particular department within an organization. So they're specialized computing devices that are geared towards particular application of a small organizational unit. Some companies use appliances as sandboxes to develop and test new applications before moving them to the entire warehouse. Some appliances are designed to handle unstructured data by incorporating various technologies that are useful for it, like Hadoop, MapReduce, and we're going to talk more about those two technologies a bit later. Oftentimes, Data Mart appliances are fine-tuned for specific applications such as retail data or call records in telecommunications firms or transactions, purchasing transactions at the supermarket. A number of technologies are used to deliver high performance. For example, massively parallel processing, this grid computing that we just discussed. Columnar databases sometimes used to speed up processing, and we'll discuss columnar databases a bit later. And all major BI business intelligence vendors, they offer appliances. That includes such vendors as IBM, HP, and EMC. Okay, analytical sandboxes, another concept, another technology that is again related to data warehouses. You see, advanced analytics can be quite costly computationally, meaning, a simple query, if it's done on a large scale, let's say you want to find information about, if you want to categorize purchases of all customers, over several years. Now, even a simple query like that can create a substantial burden on the entire data warehouse. In other words, it will use a lot of computational resources and slow it down. Now, sometimes relational database management systems, or RDBMS, they have some kind of query manager, so that all queries that come into the data warehouse, they're not launched simultaneously, something that would overload and crash systems. So this query manager allows to prioritize those queries. So that's one way to handle it. Now, another approach to handle it is to create the so-called analytical sandbox, where modelers or employees can play with advanced analytics without affecting other users. So basically, an analytical sandbox is a subset of the entire data warehouse, a copy of a small portion of the entire data warehouse, so that others can experiment with it. They can change data, they can query it all the time without impacting performance of the entire data warehouse. Now, analytical sandboxes can be real, meaning it's like a separate appliance, separate server, or they can be virtual. A partition is created on one of the servers that is a part of the data warehouse, and a copy of data from the data warehouse is made, and people manipulate it without affecting the entire databases, the entire collection of databases at the warehouse. So that's analytical sandboxes. Now, another technology that is used as a part of big data infrastructure is in-memory analytics, and we already mentioned that. Now, one of the barriers or impediments to fast response times for queries is the time required to find data on a disk and to read it into random access memory. Now, response time, the time it takes to read and load data, can be reduced 10 to 1,000 times by using something called in-memory analytics. Now, under this paradigm, under in-memory analytics approach, the data is stored in random access memory, or RAM, rather than on a physical disk. And this is quite this is much faster to store data in random access memory. There are two types of implementing in-memory analytics. Some platforms, they're geared towards that. In other words, there can be like a box or a platform, that is specifically designed to do all the processing in memory. Or sometimes there's no special platform, it's just the way an application works, it allows to do in-memory processing. Now, one example that I'm personally familiar with is RStudio or R programming language. It does processing in memory, in random access memory. Of course, it has the advantage of that is that sometimes it's much faster. However, the disadvantage is that most computing devices, most servers, most computers, they have limited random access memory because it's expensive, and also because of the way, because of its physical design, you just cannot have terabytes and terabytes of random access memory. A typical computer would have, a few gigs nowadays of RAM. So that creates a number of limitations when you're dealing with huge data sets. However, there are certain software solutions developed as a part of R, for example, that allow to distribute that in-memory processing or divide that in-memory processing, use chunks, for in-memory processing as opposed to trying to load the entire data set. Because sometimes if you have limited RAM, then the system can get quickly overloaded and crash. Now, one thing to keep in mind is that some applications are well suited for in-memory analytics. Those are the applications where it's crucial to do the analysis in real time. Maybe it's something related to security, let's say police dispatching or flight monitoring. But some applications, they're not that time sensitive. For example, let's say something related to student analytics. Of course, you want to analyze student performance in a course in a timely fashion, but it doesn't have to be done in real time because we don't deal with something that is critical. You can give feedback to students about their grades, with a delay of a few, hours, days, or weeks. So, in-memory in-memory processing may not be very suitable for this particular type of application. In-database analytics is another technology that is emerging and that is used as a part of big data infrastructure. You see, the way a typical analytical application works is that you have a database with data, and then you make a copy of the database, and then you do some analysis with that copy. For example, you find averages, or you sum all the values in a particular column. Now, if everybody is doing that, if everybody is querying this database, trying to load data, download data, then it creates a lot of strain on the infrastructure. So some analytics vendors such as SAS are partnering with database companies such as Oracle and Teradata to integrate SAS analytics into their products. In other words, databases would be capable of doing basic analytics themselves so that you don't have to do it on your own. So this is supposed to create like a more even usage of IT infrastructure. If some analytics can be done on the database side without every application doing that analytics on its side, copying the data and doing analytics on its side. So some basic analytics can be retrieved from the database itself. By the way, in this class you worked with Microsoft Access database technology, and it has some built-in analytics, like you can find like sums, averages of certain fields or columns in a table. Okay, columnar databases. It's in a way, it requires a lot of explanation because to really explain how columnar databases work, and most importantly, why they are faster than role-based databases, this is something requires a lot of explanation about record indexing and record searching in a database. But to give like a small overview. Now, historically, database systems, they're role-based. So whenever, and it's depicted right here. So whenever there is a new data coming in, let's say about a particular customer named Susan Wilson, then a record is added. Now, some tables, they have millions and millions of records, while having only a few columns. Now, what happens is that whenever there is any kind of search operation, whenever you need to retrieve any kind of record, let's say a record about Mark, every time you do that, you need to go through millions and millions of rows. So this is how traditional databases work. So some database vendors, they figure it out that it may be much faster to operate, to search, to manipulate data in a database, not using rows, but using columns. So because like here you may have, let's say, only 4 columns and then millions of rows. So it just much faster that way. But it's, again, columns are just used as a starting point. there are additional algorithms that retrieve specific data points from those columns. But again, it was figured out that doing processing at the column level may be much faster in terms of loading data and so forth. So this is the essence of columnar database technology that is once again is frequently used in conjunction with big data infrastructure. Then you have another technology or set of algorithms or set of software. It's called streaming and complex event processing engines. You see a lot of devices nowadays, they're connected to the internet, and by devices we mean pretty much anything like cars, computers, cell phones, utility meters, and so forth. So they're all connected to the network and they send data. So for example, cars may send data about their location, about status of various components, about speed and all those things. Now, when this data is broadcast, organizations are realizing that there is value. A value can be derived by receiving this data, processing it in real time, and taking immediate action based on that real-time streaming of data. By the way, this whole idea of connecting both various physical devices to the internet is called Internet of Things. Now, Internet of Things concept basically extends beyond computers and electronic devices being connected to the internet. Under the vision of the Internet of Things, you connect all kinds of objects to the internet. Cars, cell phones, kitchen appliances like refrigerators and so forth. So there are many applications of that, trying to load those streams and find some interesting events or patterns, and then do some actions based on those patterns. Applications typically include automatic stock trading. For example, based on a particular pattern of stock price fluctuations, a decision to purchase the stock can be made. Credit card fraud detection. For example, if somebody has made several suspicious transactions in a row, let's say bought concert tickets, bought pizza, and ordered, boxing match, and all within 1 hour, it's considered to be a stolen credit card, something like that. And then some patterns in supply chain management and equipment monitoring can be also identified. Now, the key here is that trying to identify patterns and act before something happens. For example, trying to block a credit card before a substantial amount of money is spent, or trying to service an equipment before it actually breaks down. There's a lot of software, there are a lot of engines for doing that, and here you have some vendors being mentioned. So it's all about detecting patterns and anomalies, and then incorporating certain rules that outline those patterns, and then trying to automatically act upon those patterns. And again, the key is to act before something happens, not after it happens. Okay, cloud-based services. Now, everybody's talking about the cloud-based services nowadays, even outside of the context of big data. So, cloud-based services are quite popular. Now, by cloud, we mean the internet, because this is the notation, this is the pictogram that is typically used to depict internet in networking diagrams. So, cloud computing involves accessing hardware, software, and data over the internet without having anything installed, on the premises of a company. So basically, another way to explain that is, cloud computing means virtualization of computing resources, and those computing resources are then accessed over the internet. Now, cloud has a lot of benefits. You can quickly access specialized resources. For example, you may not have enough expertise internally to maintain a particular piece of software, so that you can, quickly purchase that access. Quick deployment. Everything is pre-installed at the vendor side, so you don't have to deploy anything on your side. Easily expanded capacity. If you need extra capacity, extra servers, you can hire them or lease them on a temporary basis. You can also discontinue once you no longer need them. So overall, it translates to cost savings and also greater data security, because especially if you're a small company like a small bank, you may not have enough resources to maintain data integrity, to do proper backups, and to do recovery. Now, a cloud-based services vendor can do all those things for you for a fraction of what it would cost you to maintain like a full IT team doing all those things, like protecting data, doing backups, and recovery. Now, there are various variations of cloud-based services. First of all, you have an arrangement called software as a service, or SaaS. So basically, the vendor provides the hardware, application, software, operating system, and storage. So basically, everything is delivered to you over the internet. The only thing you need is to upload your own data and start using this particular application over the internet. Many business intelligence and analytic vendors, they offer cloud service versions of their software. Here you have like all those companies that offer that. Personally, I use the SaaS Enterprise Miner over the cloud. Basically, what you do, you access this powerful infrastructure using a web browser. But when I did it, it just wasn't fast enough. Maybe it had to do with my internet connection, and I think there were also some limitations as to what kind of data can be, the size of the data that can be used in conjunction with this free cloud-based service for universities. But nevertheless, it's getting popularity. Then you have something called platform as a service, where you are basically accessing not a specific application, but a particular platform. Let's say particular servers with a particular operating system already being installed. There are many examples like Oracle Cloud Computing that offer you that platform. So basically, it's like a more flexible arrangement where you lease, you temporarily rent a particular platform to install your own software. And then you have infrastructure as a service, where it's more like on the hardware side. So you get like this computing capacity, and then you install your own operating system and your own software is needed. So this is done when a company wants to have greater control over their software resources, or where they do some kind of custom operating system or custom applications that cannot come from the vendor in a cloud-based arrangement. Now, one well-known infrastructure as a service vendor is Amazon EC2. Many companies use that. Okay, friends. So that concludes part 2 of our video presentation on big data. Thank you for listening.